Hello, everyone. Nice to welcome you once more at AUA after Kodaska. So today I am presenting our joint work with Ashot Harutyunyan. We started to work on this problem at VMware, virtualization company that moved to cloud, all workloads, and we encountered a lot of problems regarding optimization of infrastructures and applications in cloud, troubleshooting. So if I try to somehow outline the entire work, what we need to remember that we have cloud, we have native cloud applications, we have a bunch of problems in cloud, because if you are going to use the benefits of cloud, you need more than just utilization of cloud. We have very complex applications. We need somehow to troubleshoot them, resolve the issues. So you need to monitor them. You need distributed tracing just to monitor these complex applications. And then just finally apply machine learning approaches just to resolve and understand the problems. Now, this is actually the problem when from machine learning you need not predictive power, but explainability, interpretability. You need to explain something, but not predict, because there is nothing to actually predict specifically for this problem. So cloud computing, distributed computing, you heard a lot about it, a lot of benefits, like elasticity, when you can just extend the overall resources when you need them. Distributed computing, it's just one of the benefits. But all these benefits are not coming just free. You need to pay for it. And usually, when you are paying just for resources, you also need to pay for complexity. Everything is very complex, everything is distributed, you don't know where your application and infrastructure is working, in Armenia, in Australia, in US, or somewhere else. So you cannot just open your server and just see what's going on within your hardware. So you need to pay this cost, and one of the costs that you are paying is actually trying to monitor your infrastructure and application in order to understand what's going on within it, how to optimize it, how to reduce the costs. And you are actually using a lot of different monitoring tools. You have many dashboards, you have just a lot of information, and usually domain experts starting to dig into these pictures, they're just directly looking into them and trying to understand what's going on. And you see that it's just useless, just activities. There is no way that you can look into these hundreds of different dashboards and try to understand what's going on there. And usually what you are getting from these monitoring systems, just different sorts of data. There are at this moment 3 data sources that we are using, known as the pillars of observability. They are metrics, tracing, and logs. Of course, you can add more data sources, like maybe you need audio, and you need different computer vision algorithms to apply to some pictures, images. But actually, monitoring tools now are not using them because they are very complicated to understand how to use them. So we are using with metrics, tracing, and logging, and today we will speak about tracing. So just forget about metrics and logging, and we have tracing. The tracing that we are specifically using is known as distributed tracing, because native cloud applications have distributed structure. So when you are comparing just classical applications, they are monolithic applications. They are just one box. And when you are trying to just use the benefits of clouds, you need to somehow distribute the microservices of your application. So you are just distributing your application into different microservices in order to use the benefits of clouds. So you have different microservices, you are just distributing them across the globe and then using the benefits of this distributed computing. And then the problems are arising because you really don't know how to monitor and how to resolve the issues within these native cloud applications. That is why we are using distributed tracing in order to understand how this distributed structure is actually behaving itself. So if you are trying to understand how distributed tracing is working, so first of all, we need to understand how trace is constructed. So trace is actually showing how a specific request is penetrating across your application. So how actually it works. So single trace is composed of different spans. Each span is actually responsible for a specific microservice. And then you can see how each individual microservice is working. For example, you can measure, for example, time. And together with time, you can have also other detailed information regarding your application microservice. So one by one, you are just seeing how your microservices are working, and as a whole, these all microservices are giving you a single service. Ideally, if you are a really domain expert with a bunch of eyes and brains, then of course you can just use some browsers, you can just collect all your traces and one by one just look into the errors and try to understand how your application is just behaving. But you cannot do it because within a second you will get millions of different traces. Some of them are coming with errors, some of them are normal. So different traces are coming from different microservices. There can be hundreds or thousands different microservices. And you just stuck here because there is no way that you can continue. So the only way that you can continue is somehow apply artificial intelligence, smart solutions, etc. So something that can help you somehow to automate the entire process. And you can see why, because this is your application. This is how your application is behaving. So you have many different microservices. These microservices are distributed across the globe. You don't know their physical details, which one is working how and where. And that's it. You are just standing and looking on such pictures without knowing how to continue. And then what you are doing, just implementing some metrics, they are known as red metrics, responsible for errors, for request rates, for durations of the traces. Then you are just monitoring them, putting some thresholds, trying to understand how many errors you have, from where your errors are coming, and then you are just coloring your microservices. You see there is one red just microservice saying that, for example, the percentage of errors is much higher than you were expecting here. How we are transforming this problem to a machine learning problem? We are selecting this specific microservice, selecting all traces passing through that specific microservice, getting some data set of labeled data, and then trying to apply machine learning approaches for somehow understanding the behavior of your traces. For example, assume that you have some traces and you know which ones are coming with errors, which are just behaving typically. Here, the problem that I have described, that actually you don't need predictive power. You need only explanations. Let me explain it in more details, because when a trace is arriving, usually a trace has a label. It is saying that I am coming with an error because developers are already somehow put that errors in the code. And there is nothing to predict. The only thing that you are trying to do is just to explain why this error is coming to you, why your microservice has this bigger percentage of errors compared what is normal. That is why nothing to predict, because you already have those predictions. The only thing that you need is to explain. And that is why you need explainable AI methods. Something that will show which component of your microservice, which feature is actually behaving anomaly, and why. So maybe putting some thresholds on your features and trying to explain, for example, this specific microservice is malfunctioning because it is coming from Australia, for example. You need to understand why. Is it connected with a specific user, or is it connected with a specific application code, or is it geolocation or something else? So one of the powerful explainable AI methods is actually known as Reaper. This is rule-induction approach for classification. So you are trying to classify your errors versus typical traces and just not predict, but trying to explain. Reaper is very powerful. It has some benefits for us. For example, it is dealing with missing values because our data sets are totally coming with missing values. 90% of our data sets are just empty lists. Only 10% is composed of some useful information. Then it is dealing very well with overfitting. So it's just not overfitting, it's just getting to some rules without overfitting. It's very scalable. It's linearly scalable. So if you have a bunch of traces, then it is just taking seconds to execute. And the idea of Reaper is just separate the corresponding classes, and for each class show a specific rule. Rules are usually coming in this form: if, body, then condition. And you see which features are important for your application, coming with what kind of thresholds. One of the Reaper output showing here. So one of the efficient implementation is known as JReap. This is Java Reaper coming from Veka library. So if you want, you can just download it and use. It's free. And JReap is actually showing different microprocesses, microservices, saying that, you know what, if you had, for example, 3 health VPXD, Vim session manager logout span, or in other words, microservice in your trace, then the corresponding output will be coming with error. So it's just explaining the errors. And it's saying, for example, that he found 868 different rules and only 17 were misclassified because they are not connected with the errors. So it's just exactly showing which microservices are actually responsible for the current malfunctioning situation, and then giving some numbers that you can use to compute precision and recall for this specific rule. And then you have the second recommendation, then you have the third recommendation. In this particular example, you see just simple rules. And you have list of recommendations saying that, you know what, there are several microservices that are somehow connected with the errors that explaining malfunctioning of your specific microservice. So based on these numbers, you can actually calculate the corresponding accuracy. For each rule, you can calculate the corresponding precision and recall. And then you can just sort the corresponding rules by the confidence or maybe by precision, recall, it depending what goals you have, and then sending top 3 or 5 recommendations to a user. Then system administrators, knowing this information, can follow to understand how to perform different remediation tasks, because we are exactly showing which microservices are actually responsible. And you see that output 1 are all connected with the errors, and then output 0 is just the remaining rule saying that the remaining traces are just normal, and you have misclassification or only 84. So based on this, you are just calculating the accuracy. In this case, it's just more than 90%. Unfortunately, not always Reaper is giving very accurate recommendations, because you know, when you have highly explainable approach, then you are suffering from predictive power. But in cases when it is giving you rather high accuracy, you can rely on the corresponding rules. And then more interesting rules. with much more details. For example, you see the first rule is actually saying that there is an error type, and specifically showing that, for example, Vim fault not authenticated is the error type that is explaining malfunctioning of your microservice. So not only showing which microservice is actually malfunctioning, and showing also the error type. And you see, for example, the corresponding rule is saying that add 5.1 fired rules and no any misclassification, 0. So it's just with 100% confidence actually explaining that specific error by that specific rule. And then if system administrators know actually what does it mean to have this not authenticated error type, that you can go and resolve the corresponding problem. So usually when we are dealing with this kind of applications, we are applying several scenarios. We can use spans, these are just description of microservices, or we can go just into details. These details are known as application tags. You can just look into the durations, you can just look into geolocations, some IDs, some links. So getting more detailed information from the distributed tracing that is actually giving you. And then how this entire scenario is working. So you are just clicking the corresponding microservice, internally calculating all possible traces passing through that microservice. It is known as trace traffic. So you are just investigating the corresponding trace traffic. And on the right, you are getting the corresponding recommendations. So you can have top 3 or top 5 recommendations. Actually, specifically for this example, the execution time is just a second. So you are just clicking a button, and after a second, it's giving you some recommendations. So these recommendations are not usually for a user, because users don't know what's going on there. But it's a support for domain experts, for system administrators, who directly can understand what's going on within an application and how to remediate the corresponding issues. Now some items regarding future work and regarding the problems. So Reaper is powerful in terms of explanations, but it's suffering from predictive power. And you see, for example, in some interesting examples where other methods are giving you something, the list of rules are just empty. The lists are empty, there is nothing to show. This is due to predictive power. You need more powerful approaches. Or even when Reaper is showing you some rules, then the accuracy is only 53%. If such, then you cannot rely on the corresponding recommendations because they are suffering from accuracy. So in some of other works with Ashot, we try to implement more powerful approaches. For example, boosting approaches, decision trees, etc. They are giving much more accurate solutions, but they are suffering from explanations. That is why we are trying to apply external explainable approaches like SHAP, like Lime, or permutations-based approaches. And what is interesting, in this particular example, when you see empty list of recommendations, other boosting methods are giving 100% accuracy. Of course, they are suffering from explanations because they are just showing some features, but not showing the rules, not showing the thresholds. So they have lower explainability power compared to predictive power. But in any case, this is trade-off about which you need to think when you are solving such problems. So what you need? Highly explainable approaches with less accuracy, or methods with highly predictive power but less explainability. So it depends on the domain in which you are working, actually. And we are continuing this work, trying to understand what more powerful approaches we can apply here with some additional explainability. Thank you. If you have any questions.
If I understood it right, you say that the system works in such a way, tracing, looking at the results, and repairing by system administration. Just in 1-2 seconds, it is done overall. But I say, what is the future of that system? Is it right? For example, for the future of medicine, it is tracing, repairing, and improving. And all this in doing it almost simultaneously. Can we say that this approach is appropriate for that, for cloud, for security of the cloud? That is tracing and repairing all this and drawbacks and vulnerabilities in the system, and improving almost simultaneously, doing that based on AI system, for example, which estimates all the results, simultaneously improving, repairing, and improving the system.
So honestly saying, even with AI, there are no ideal solutions. So you cannot think that just working without you, without an expert, and just resolving all issues. This current tool is now productized at VMware. We are using it, but it's not just ideal solution. It's just giving you some recommendations. How you are going to use these recommendations, it's on you, on domain experts. You cannot just forget about it, and it cannot resolve all issues that you have. You need to read the recommendations. You need to understand them. If you are understanding them, then they are giving you some remediation path. If not, then you are just ignoring them. They are something like a support, nothing else. But currently they are working. We have several customers using this approach, rather big customers who have just huge cloud applications with millions of different traces, with millions of with not millions, but with hundreds, thousands of different microservices, because they are distributed. One microservice can have replicas, thousands of different similar microservices. They are using it, somehow helping them. I will not say that they are very just happy with it, because this is AI, this is reality.
So I'm interested in what's the complexity of this Ripper algorithm. Like, for one of the examples you showed, it's 17 seconds, and I don't really know was that a big system, was that a small system, how long can it actually take, and what does it actually limit? Is it computation or is it memory?
The complexity is directly connected with the number of traces that you are using, and within these traces, for each trace, you have number of spans, and within each span you have number of tags. So this is actually the size of your data set. So if you have, for example, 10,000 different traces, so these are the rows of your data frame, and you have 1,000 columns, so 500 spans and maybe plus 500 tags, that's approximately 10 seconds. This is how it works. Without any GPUs, just totally on CPUs. And just it's rather fast because 10 minutes is the time that our users are ready to wait. So we have 10 seconds. So actually 10 seconds. If after 10 seconds you are not showing the results, you are not showing them never, because users are waiting just 10 seconds. If within 10 seconds you are showing some recommendations, it's okay. If no, then you are saying there are no any recommendations. But for smaller data sets, it will take up to 1 second, even working for milliseconds if you have, for example, several hundred traces. But Reaper is usually connected with the noise. If you have exact classes and you can find some rules, it's very fast. If you are working with noisy data sets, of course, it's adding some complexities usually. But actually, people are saying, who are working on this Reaper developing it, saying that it's connected linearly with the number of traces. So it's rather linear approach, rather powerful. The problem is the predictive power. You cannot always rely on it. When you are showing some recommendations, you need to check, do you have sufficient accuracy? Because if not, then just forget about the recommendations. You cannot rely on them. This is the problem with rule-induction methods. Yeah, for example, we have a specific problem. We have a bunch of missing values. So in our data frames, 90% is coming with missing values and 10% is some useful information. So for example, there are no such many methods that you can apply in this case. For example, there is no way to apply neural networks. So you are somehow limited. You need to take approaches which are dealing with missing values. Repair is one of them. Decision trees are one of them. Boosting is one of them. So boosting is usually giving ideal results, 100% accuracy. The problem is that with boosting, you can get only importance of features, nothing else. So you are saying this specific feature is very important for you, but within this feature, you have many different categories. Which category is more useful for you? You don't know. So when you are comparing with Reaper, Reaper is just giving you ideal information, not only feature, the name of span, but also some additional details, saying, you know what, this specific customer is causing some malfunctioning within your application. So there are some limitations that you need to think always. Missing values, some other limitations, explainability versus accuracy, and there are some restrictions here. Thank you. Okay, go ahead.
If you use more rules than 7, they are increase your accuracy.
So actually, we are not controlling the number of rules. Reaper is automatically selecting based on some overfitting limitations. So you're just optimizing rules until you are not overfitting. And you really don't know how many different rules you will get. Maybe 0 number of rules, maybe 1, maybe 100. But it's very strange if you are getting 100. Because for each rule, you need to calculate the corresponding coverage and confidence. And you're just skipping the rules which have smaller coverages or smaller confidences. So eventually, you are ending up with 1 or 2 recommendations. And from the other side, user cannot read just 100 different recommendations. He's just trying to see only one useful recommendation that he can use for a remediation procedure, nothing else. If you have more, then it's not working. Okay, thank you.